to take a little bit of a shift now. So we've been looking at primarily low temperature thermochronometry, and uranium-series can be sort of indirectly related to that, but it's not a thermochronometric method. There are a number of applications that pretty much span a lot of geology, the one limitation being that it has to be young, in the order of sort of 1 million years or so or less. But you can use U-series to look at everything going from magmatic processes to carbonate dating. Carbonate dating in itself has a number of applications ranging from paleoclimate reconstructions from speleothems, paleoseismology, neotectonics, archaeology, and so on. U-series is used in oceanography and hydrology. There's a number of other applications that I haven't put on here. U-series has been instrumental, for example, in helping calibrate the carbon-14 scale. I am not in any way going to do justice to all of these different applications. What I'm going to do in this talk is go over some broad sort of concepts that apply broadly to U-series in general and how the system works in general. And then for the applications, what I'm going to focus on is the magmatic processes, because that's what I personally am more invested in. And then I'm going to touch briefly on a little bit of the vagaries of the different age equations you use for carbonate dating. Okay, so in comparison to other radiogenic isotope systems, there's a number of key distinctions. The first and most important being that what we're dealing with is a decay chain rather than a simple parent-daughter pair. And so for each of the intermediate nuclides that we use, there's a balance between ingrowth from the parent, the immediate parent, and decay of the produced daughter itself. So there's this balance when you're actually measuring the abundances of these different things. And it's that balance that we make use of in terms of trying to use these to date different geologic events. And the second thing that's certainly different from things like uranium-lead is that it's a relatively short half-life. So the half-lives vary throughout the chain, which I'll go into in a minute. But things change quickly in U-series. And most of the parent-daughter pairs that we use, we can use them to access events that occur from, say, years to a few hundreds of thousands of years on that sort of a time frame. So we're looking at things that are relatively short, geologically speaking. As a consequence of that, although the U-series nuclides aren't themselves very sensitive to diffusion most of the time, this is a similar timescale to kinetic processes like diffusion and crystallization. So when we're going from a date and interpreting that as an age, we have to consider a lot of these things about what is the history, of course. You know, there's a common theme that we've seen in the last couple of days. You always have to consider what you're actually measuring. Okay, so here are the uranium-238 and uranium-235 decay chains going to their stable lead daughters. And for most of uranium-lead geochronology, you can safely ignore everything that happens in between, except for, as I believe Mark probably alluded to, the case where you're trying to use uranium-lead to date very young things, in which case you have to take into account that you might have started off with an initial excess or deficit of some of these daughters, which will lead to a resultant excess or a deficit of the ultimate daughter. And that is proportionally more important for young systems and young grains than for old things. Now, within the U-series decay chain, any uranium-bearing substance, if you leave it alone to its own devices for a long enough period of time, and that translates to a few hundreds of thousands of years to a few millions of years, something on that order, it'll attain a state known as secular or radioactive equilibrium. In secular equilibrium, the activity, that is the number of decay events per unit time of each of the nuclides in the chain, is equal. So you start off with the number of decay events per unit time for uranium-238, which will be the same as thorium-230, radium-226, and all of the intermediate daughters, and so on. And activity is conventionally denoted by parentheses around the chemical symbol. Now, the activity is proportional, obviously, to the number of atoms that you have present and the decay constant. Okay, so the more atoms you have present, the higher the activity. The higher the decay constant, the larger the decay constant, that is, the shorter the half-life, the higher the activity. Now, when you're talking about any given parent-daughter pair, the way a system attains secular equilibrium, you can't change the decay constant, so you have to do it by changing the number of atoms that are present. And that's how any given system adjusts itself to secular equilibrium. So that, for example, a relatively large number of atoms of a long-lived nuclide, like 234 uranium, will have the same overall rate of decay because each one of these atoms has a relatively low probability of decay per unit time. That'll produce the same overall rate of decay as a smaller number of atoms of a short-lived isotope like 226 radium, where each of those atoms has a relatively high probability of decay per unit time. So the system will adjust through the mechanism of the number of atoms present, and that means that if you can assume that a system is in secular equilibrium, you know what the ratio of every parent to every intermediate daughter is in terms of the number of atoms. Okay, now that's a particularly useful constraint, because that means that if we start off with a system that has been undisturbed for a few hundreds of thousands of years or a million years or so, we know what the initial conditions were, and this gives us an initial condition from which to measure any disturbance. Now, the other thing that's interesting, of course, is that there are different elements that are represented by the different nuclides in the decay chain. So different geologic processes will fractionate one element from another. That'll disturb an initial state of secular equilibrium. That starts the clock, if you will, and then you can measure at some intermediate time then what's the activity of 230 thorium, for example, relative to 226 radium, and you can see whether it is in or out of secular equilibrium. If it's out of secular equilibrium, you know something about the starting conditions, then you can know something about the time. All right, so secular equilibrium, the most common way to visualize what's going on with secular equilibrium is one of these sort of bucket diagrams. I'm showing here the example from Mary Reed's 2008 Elements article. So at secular equilibrium, you have this balance for any given intermediate daughter between production from its immediate parent and its own decay. If you disturb this, like for example, if you remove a certain amount of thorium relative to uranium, then you will have this initial disequilibrium state. You will have the thorium gradually growing in by production from uranium-238 as it's decaying away, but the rate at which it's decaying away is proportional to the number of atoms that are present. And so you have it produced more quickly than it's decaying away until it once again attains the state of secular equilibrium. And conversely, if you decrease the amount of uranium, it'll adjust by decay of thorium. Here's another way to look at that process. So what I'm showing here is this is an animation of uranium-series disequilibria. I'm looking at the first few daughters in the 238 uranium chain. And what I'm showing here is sort of an initial condition where you've got 238 uranium in equilibrium with 234 uranium. And these tiny little dots here represent effectively 0 of the daughters, 230 thorium and 226 in the initial conditions. Now, what I'm showing here is that the size of the circle is proportional to the number of atoms that are present. In this case, it's actually proportional to the log of the number of atoms that are present. Otherwise, this would end up being larger than this room. And then the color represents the activity. So cooler colors are lower activity, and warmer colors are hotter activity. So these are the same color, they're the same activity, they're in secular equilibrium with each other. This would be appropriate, for example, for an igneous system. Now, if I start the clock then, so after this disturbance, let's say you had a crystallization event, you removed all of the intermediate daughters, you left only with uranium. This is what would happen as you let it grow in. And a couple of interesting points here. First of all, you'll notice that things happened very quickly right at the beginning. The number of atoms that were present and the color, that is the activity, changed very quickly for both uranium and thorium. And they very quickly came to equilibrium with each other. That is, they achieved the same color, the same activity. So this illustrates the fact that for any given parent-daughter pair, what controls the return to secular equilibrium is the half-life of the daughter. I'll show you that mathematically when we talk about the particular equations. And this is also illustrating the fact that we went through the cool colors very rapidly, and then we spent a lot of time in various shades of red. So this also illustrates the exponential nature of the approach to secular equilibrium. Okay, so what that means in practice is that you have a different age range for each parent-daughter pair that you're looking at. So going from any initial disturbance, just modeled here as initial doubling of the daughter or complete removal of the daughter, for example, there is a period of time over which the change in the number of atoms that are present is too small to detect, and that's represented by this relatively sort of horizontal line here. There's a period where you have rapid change. This is the sort of useful time range of these chronometers then for each parent-daughter pair. And then it returns to secular equilibrium. And after it returns to secular equilibrium, nothing happens. And so you lose the age resolution of the technique. So what that means is that you can look at, for example, lead-210 versus 226 radium, and that'll give you sort of time scales on the order of a few years to a few hundreds of years. Radium-thorium is a few decades to a few thousand years, and so on. So each parent-daughter pair then gives you a different time range that's accessible. All right. So we've seen a number of versions of the decay equation. This is the particular version for uranium-series. And this particular formulation is showing a parent labeled number 1 decaying to a daughter, where 0 is the initial. You can also write versions of this for a parent going to a daughter, going to a granddaughter, and you can mathematically add as many daughters as you want arbitrarily down through the chain. It gets sort of exponentially more complicated as you do that, so I'm just showing the first couple of them. So for the equation in general, though, the daughter that's present at time t has two sources. It's the daughter that was present initially, minus decay of that daughter, plus the ingrowth from the parent, so that's pretty standard. But here you have the ingrowth of the parent, which is this n1 e to the lambda 1 term. And you also have the daughter decay that has happened since that parent grew in, which is the n1 e to the minus lambda 2t term here. So you have to account for both the daughter that was present initially and its decay, plus the daughter that's being produced by the parent, and whatever proportion of that is decaying away over the time frame that you're interested in order to understand how much is there at time t. Now for carbonates, the actual age equation that you use is a form of that one that I just showed you, except that it includes additional terms because for carbonates, you have to consider uranium-238 decaying to uranium-234, which decays to thorium-230. So you have to have the parent, daughter, and granddaughter all in one equation. And the equation that you end up with is something like this. It's a little bit messy. You have to solve it iteratively, but it can be done. And one of the interesting functions then is because you have two different parent-daughter pairs when you're dating carbonates, you can write a second equation, which is this delta 234, which is really just a measure of the 234-238 activity ratio. The delta 234 tracks the uranium-238-234 disequilibrium. This equation tracks the 238 uranium-230 thorium disequilibrium. So you have the two parent-daughter pairs. So with these two equations, you can solve uniquely both for time and for the initial delta 234. The initial delta 234 is useful because you can use it, for example, in corals. You know what the initial delta 234 should be because it should be like seawater. So you can use it to check for there's been disturbances. For groundwater applications, you can see what the delta 234 is, and you can use that to track various groundwater applications. Okay, so when you're looking at igneous systems, we go back to this. And in igneous systems, we can generally assume that uranium-234 and uranium-238 aren't fractionated from each other by igneous processes. And we also generally assume that any source of partial melt is old enough that it itself will be in secular equilibrium. So we assume secular equilibrium between uranium-238 and uranium-234. So we take this equation. We can also make a number of useful simplifications to simplify this equation when we're dating minerals in volcanic rocks, for example. And so going from here to here, which is a little more simplified equation, we make two assumptions. One, the half-life of the daughter is much shorter than the half-life of the parent. In this case, we're talking about thorium-230 relative to uranium-238. So we've got a half-life of 75,000 years compared to a half-life of 4 billion years. And that's a pretty safe assumption. That means that in this term here, lambda 2 minus lambda 1 is effectively approximated by lambda 2. Then we can take and multiply through by lambda 2 and convert these to activities, which is an easier thing to deal with. And then the second assumption that we make is that the time that we're interested in terms of dating, is short with respect to the half-life of the parent. So in other words, if we're looking at things that happened on the order of something less than Earth history, we can assume that this e to the negative lambda 1t term goes to e to the 0, and that converts this into this form here. So what that means in practice is that we actually measure the abundances of these elements. We can convert those into activities through the decay constants. And then we have an equation that's dependent only on the half-life of the daughter. In practice, when we're actually dating, say, volcanic minerals, we take that equation, which is the top part of this, normalize it to, as is conventional, a stable, or in this case, a very long-lived isotope of thorium, and we come up with an isochron equation, which again is the activity of thorium today relative to thorium-232 is the ratio that was there initially, accounting for decay, and then the balance between ingrowth and decay, from ingrowth from uranium and subsequent decay. So there's an equation of the form y equals mx plus b, and then the age is proportional to the isochron slope, as in other isochron applications. Now, one thing that is, or a couple of things that are different when you're actually using this as an isochron application from more conventional things like, say, rubidium-strontium, there's a couple of key differences. First of all, we're plotting activities rather than atomic ratios. And what that means in practice is that the abundances that you measure here are weighted by the decay constants. So things don't move. You don't have one decay of 238 uranium atom producing one atom of 230 thorium. You do, but on this scale, it gets magnified into a much larger displacement on this axis than this axis because it gets multiplied by the decay constants. And so what that means is that the isochron slope changes rapidly at the beginning and more slowly at the end. So it increases at an exponentially decreasing rate as you approach secular equilibrium. I'll show that in an animation next. And the initial ratio, rather than given by the y-intercept, is given with the intercept with the equiline, which I'll show you on the next diagram. I just want to put this up here as a historical note because this, as far as I know, is the first usage of the isochron diagram in igneous systems. Claude Oleg in 1968 took some data that had been published previously and plotted them up like this, which has been a very useful form. Okay, so here is an animation of a thorium isochron. What you would expect is if you have some melt, for example, here, you crystallize different minerals from it. They are, in general, going to have different affinities for uranium relative to thorium. You'll get different uranium-thorium ratios initially. They will incorporate thorium in the isotopic composition that is present. So you'll start with a horizontal array, like you do in any other isochron system. When you start the clock, then, each of these will try to reattain secular equilibrium, which is represented by this one-to-one line that is equal activities of parent and daughter. And at any given point in time, then, you have, if you stop the clock by, for example, measurement, if at some point in time you measure it, you should expect a linear array. The slope is proportional to the age, and the intercept here gives your initial thorium isotopic composition. Now, the usual assumptions for isochrons apply, I should note. You have to assume that all the phases crystallized at the same time from the same liquid and that it hasn't been disturbed since then. It's remained a closed system. Now, this is where things get complicated. So if you're looking at uranium-thorium, things are relatively straightforward. If you look at radium, things get a little bit more tricky because we don't have a long-lived reference isotope for radium. The longest-lived isotope that we have is the one that we're using for dating. So we have to have something else that we use as a proxy to normalize things to be able to calculate these ages. And the closest chemical analog is barium. So traditionally, we've used barium as the analog for radium when normalizing in this kind of isochron approach. But in that case, originally it was simply assumed that it was close enough that we didn't have to worry about any differences between the chemical behavior of radium and barium. In fact, it's been shown both theoretically and experimentally now that there are differences in the partitioning behavior of radium and barium that are significant at the level that we're interested in for dating applications. And so you have to account for this difference in fractionation. So just to demonstrate that, this is a theoretical calculation based on elastic strain model of partitioning. But for CPX or plagioclase, you expect that you see that the barium here, if you look at where radium would plot relative to barium in terms, it has a slightly larger ionic radius, but that slight difference in ionic radius would translate to an order of magnitude or more difference in the partition coefficient for radium compared to barium. So you have to account for that difference if you're going to get an age. So what that means is that rather than the system behaving in a relatively straightforward and predictable way like this, where you have a straight line array at intermediate times, you're going to start off with differences in the partitioning behavior of radium and barium that result, as well as thorium and barium, that result in different initial radium to barium ratios in your phases at time 0, and that will be basically propagated through, so you'll end up with these kinked or nonlinear arrays on an isochron diagram. So this makes the isochron diagram less visually useful for conceptualizing ages, but as long as you can correct for this initial deviation from zero fractionation between the two of them, you can correct for that and you can still calculate an age. However, it's important to realize that those are always model ages that are dependent on how well you know the partitioning behavior. Okay, so here is then how a radium isochron evolves over time. You can see everything still attempts to attain secular equilibrium. The time scale is shorter for attaining secular equilibrium. Where am I? Than it is for thorium. But still, if you measure it at some intermediate time, you can still extract age information from these. You just don't expect a linear array to be preserved. Okay, so the other effect of that, though, is that mixing between different phases, as for example in incomplete separation of minerals when you're doing your mineral separates, or inclusions inside your grains, or here's some melt inclusions and plagioclase inclusions and pyroxene, mean that rather than simply mixing along a straight line array, as you would in the thorium system, if you mix phases along a straight line array in the thorium system, you change the resolution of your age, the resolution of your slope, but you don't change the slope, and so you leave the age that you would calculate the same, the date that you would calculate. In this case, if you mix between, say, pyroxene and plagioclase and melt at zero age, you'll end up somewhere in the middle here, and the date that you would calculate for the CPX that's a mixture is different from the true zero age of the mineral phase. So there's two approaches to this. First of all, then, you have to make sure your mineral separates are as pure as you can get them. But there's always the problem of inclusions, and I should point out, and we'll talk about this a little bit later, when you're talking about an age for dating volcanic minerals, you typically need sample sizes that are on the order of grams of mineral separate. So it's impossible to separate out all the inclusions. You can't take the approach of carefully picking out the grains that have no inclusions, because it would take you a decade to get a sample. So we have various ways to work around this. You can do, for example, laser ablation or ion microprobe analyses of the pure mineral and use that, compare that with the trace elements that you measure in the solution that you actually dissolve, that you're dating, and then you can calculate what the pure concentrations of these elements would be in the pure mineral by mass balance. So we can account for this, but again, it adds uncertainty to the whole thing. All right, so what we do for calculating a model age, first we correct for impurities. We determine partition coefficients that are appropriate for the conditions in mineral that we're interested in. And then we calculate model ages. And as I alluded to, an isochron diagram is not particularly intuitive in terms of determining what is and isn't a consistent age array. So we use an evolution diagram where we plot years before present versus the radium-barium ratio and how that evolves. And you would expect for coexisting pyroxene and plagioclase, they would at some point in the past have a composition that was in equilibrium with the melt that they crystallized from if they all crystallized from the same melt at the same time. And so this would be the age that you would calculate. All right. The bottom line then is that, as with all of these techniques, it's complicated. You have to know what you're doing. But it is orders of magnitude more complicated to do radium dating than it is for uranium-thorium dating. So if all you're interested in is sort of a bulk age and you're in the appropriate time frame, thorium dating is much, much simpler than radium dating, which is why very few people are doing radium dating anymore. Okay, practical considerations. What do you have to do to actually get these measurements, these dates? So what do you need to do to prepare the samples? How much sample do you need? How are they analyzed? And importantly, how long does all of this take? So the workflow for a bulk sample, so a bulk separate of a major phase or carbonates or something, you collect it. You either do a mineral separation, or in the case of carbonates, you would drill out the interval you're interested in dating. Here's a picture of me in the field in Iceland collecting a sample of this basalt lava flow. This set of bags here is about 3/4 of the size of the sample that I'm going to actually end up processing to get mineral separates to date plagioclase in this basalt flow. So it's relatively low abundance in plagioclase, and you have to get extremely pure separates. So you start out with a lot of stuff in order to process it for weeks to months to get down to the point where you have a little vial of pure plagioclase, for example. You take that, you dissolve it. Typically we use a microwave dissolution system because we're dealing with a lot of volume of material. Run it through columns. In the case of uranium-thorium, you go through about 2 steps of column chemistry. In the case of radium, you go through 9 steps of column chemistry. And then you take all of those separates and you measure them on a mass spectrometer. In this case, the instrument of choice for doing most of this stuff for the solution work is a multi-collector ICP-MS. And we end up, to calculate a date for thorium, we need to measure thorium and uranium concentrations, thorium and uranium isotopic compositions, each of which is a separate measurement. And if you're going to do radium, then you also have to measure the radium concentration and the barium concentration as well. So you end up doing somewhere between 4 and 6 different measurements, each of which takes a relatively small amount of time on ICP-MS, somewhere between 15 minutes to 30 minutes. But when you take into consideration the number of different measurements that you have to do and the running standards for quality control and all of that, you could expect ballpark to spend somewhere on the order of 5 days of instrument time to get a set of 10 samples where you get all of these requisite measurements. Okay, so for in situ measurements, the mineral separation and collection is similar, a little bit more straightforward. Generally, it's easier to get a pure separative zircon, for example, than a pure separative plagioclase. The grain mount, so there's no dissolution. You skip all that messy chemistry part of things, which really saves a lot of time. So you mount them up on a grain mount. A recent development has been that in the last 5 years or so, people have started doing different kinds of grain mounts for in situ measurements by laser ablation or ion microprobe, where, say, for example, if you have a zircon crystal, you can either mount the unpolished zircon in an indium, precedent indium metal, for example, and measure the unpolished surface. That gives you the last stage of crystallization. And then you can take that same grain and remount it in epoxy and polish into the interior and get another age spot on the interior. And that allows you to get much higher precision on the last stages of crystallization because your ion probe pit is oriented so that the width goes along the face rather than the width of the spot crossing multiple zones within the interior. So you have the sort of width of the spot oriented perpendicular to the growth axis, and you can get much higher spatial resolution on that last stages of crystallization. And then you have thorium and uranium isotopic compositions measured on some sort of an ion microprobe, typically. Some people have done it by laser ablation as well. Okay, so how much sample do you need? If you're doing it in situ, you need something on the order of tens of grains to get a statistically significant sample. If you're doing carbonates, typically analyze somewhere around 100 to 500 milligrams of sample. If you're doing bulk mineral separates, depending on whether you're doing just thorium, you can get away with a few hundred milligrams of sample. If you're doing radium analyses, you need something on the order of a few to 5 grams of mineral separate, which looks like this. So you have a vial that's about that big that's mostly full of pure plagioclase. And how long does that take? As we've discussed, the mineral separation is really one of the most critical, probably one of the most time-consuming, but also one of the most variable phases of this. It can take anywhere from, say, a day to do a zircon separation for a small sample, to weeks to months to do a good separation if you're doing the bulk mineral separates. For radium, for example, the in situ work, the preparation of the grain mount and imaging takes a few days, and the analyses take about 40 minutes per spot. For the bulk separate ages, the sample dissolution in chemistry takes anywhere from 2 to 6 weeks, depending on how well you know what you're doing and whether you're doing just uranium, thorium, or whether you're doing radium as well. And then the analyses take somewhere between half an hour and 1 hour per analysis. But when you consider that you have a bunch of these analyses that you need to do, it takes on the order of half a day of instrument time per sample. And then the carbonate dating, sample drilling and cleaning, about a week, dissolution in chemistry, 1 or 2 weeks, and the analyses take somewhere between 2 and 4 hours of instrument time per sample. Okay, so what I'll be talking about in terms of the applications is simply the magma reservoir processes, because that's what most of my research is focused on lately. I have been working on getting carbonate dating set up in my lab. It's not quite ready for public consumption yet, but hopefully we'll be getting there pretty soon. Most of the igneous applications that I and my research group have been looking on are centered around the question of what does a magma reservoir look like? Okay, so does it look something like this, where you have this giant open tank of magma, as is shown on the Yellowstone National Park website? Or do you have something that looks more like this, where most of the magma reservoir is actually only partially molten, some sort of a crystal mush with a sort of young granitoid, even completely solid around the edges, and the eruptible high liquid fraction magma is only a very small percentage of the total magma reservoir. You can probably see where I'm going in this, but I'll try to convince you over the the rest of this, that what we're seeing is evidence more of this state of affairs than this state of affairs. So the kinds of questions that we're interested in asking are these, and these have obvious sort of linkages to understanding, being able to date the crystals and understanding the crystal ages. This is certainly an obvious link between why we'd be interested in dating the crystals. It turns out that the physical state, we can actually, by having the time constraints that are given by crystal dating and coupling this with those other thermal constraints, we can talk about the temperature, the crystallinity of magma storage, and bringing in other types of information. Doing these kind of things with multiple samples, we can look at how magma reservoirs vary chemically and thermally over space and time. And we're interested in questions like, what are the reservoir dynamics, and are they similar for systems of different size and different composition? All right, so what I'm showing here is a compilation that I put together for a review paper that's currently in review as a Geological Society of London special paper. And this is, I won't claim that it is every single U-series date on a major phase in a volcanic rock, but it's pretty close. Probably captures at least 90% of them that are out there. I did a pretty exhaustive literature review. The light blue are uranium-thorium isochron ages, and the dark blue are radium-thorium model ages for different samples. And these are seeing where they're coming from. In general, each one of these spots represents an isochron for either a single mineral or multiple minerals in a given sample of a given rock. Okay, so what you can see in terms of stepping back, broad patterns, most of these have the dots represent the most probable age. Most of these have ages that are on the order of a few thousand years to a few tens of thousands of years. So thousands of years to a few tens of thousands of years. All of the radium ages are in this window. That's simply because by the time you get over 10,000 years, you lose the age resolution because it's back in secular equilibrium. But there is still, if you look in detail between, say, for example, the thorium ages and the radium ages of the same samples, they commonly show discordant uranium-thorium ages and radium-thorium ages. All right, so that indicates a complex crystallization history for the minerals. And here's how that works. So if you have a model magmatic system and you have crystals that are growing in pulses, so let's say every 10,000 years you add some growth to a crystal population, what you'll do is that during this initial stage where you've just had one single phase of growth, you'd expect concordant uranium-thorium and thorium-radium ages for the apparent ages that you would calculate. But as soon as you have a second phase of crystallization, both of those apparent ages average out that older and younger crystallization, but they average it differently. And so both will get younger, but the radium is more sensitive to the younger stages of growth, and you'll get a younger apparent age for radium than you would for thorium on the exact same sample. And that pattern then continues, and they diverge more and more as you get multiple pulses and longer periods of time. So the converse of this is that if you measure, if you date a crystal, a particular mineral separate with these two techniques, and you get discordant ages, it implies that there's been something other than a simple crystallization history, a single phase of crystallization followed by decay. Okay, so it requires this combination. That's very useful because it means that we can actually then turn this around and extract more information from the system. So I want to spend a few minutes looking at the question of what fraction of time do magma reservoirs spend mostly liquid versus mostly solid. Okay, and the way we do this is by combining crystal ages with other chemical records. And so we combine the crystal ages, which are largely insensitive to temperature, with other temperature-sensitive information. And the motivation for this is the same compilation of uranium-thorium and radium-thorium crystal ages, but now I'm also plotting on different chronometers, so crystal size distributions, which give you something about the total growth duration, and diffusion ages of trace elements within these crystals, which are, broadly speaking, all of these temperature-sensitive chronometers give you much younger ages than the radiometric ages for the same samples. This has been recognized for a long time. What we did is to recognize that this offers us an opportunity to extract some information about the thermal history. And here's how that works. So if you have a magma reservoir going through some complicated thermal history related to sort of from the time of first crystallization of the minerals that you're dating, maybe the reservoir cooled down, it could have heated up due to injection of a new magma, had some other cooling and subsequent heating and so on. And so it basically spends a lot of time bouncing mostly back and forth between the liquidus and the solidus with occasional excursions. You can get the total amount of time that these crystals are recording by dating the crystals. So that defines this time frame and gives the context for everything else. You can get then the time that it spent in between the liquidus and solidus, or more technically speaking, in between saturation in the mineral that you're looking at and the solidus, by looking at something like the crystal size distribution, so that constrains the amount of time it spent in between these two temperatures. Or you can get, for example, the diffusion times, where you can, for an arbitrary temperature, if you have a trace element profile that's not in equilibrium, you can calculate how long it could have spent at that temperature before that diffused away to equilibrium with the surrounding liquid. So if you have initial disequilibrium, which is very common, you can constrain how much time it spent above a certain temperature window. And then finally, the fact that we have these crystals at all means they didn't spend a lot of time above the liquidus dissolving, so knowing dissolution rates, we can calculate how long it could have spent at extremely high temperatures. And then, because we have this U-series age of the crystals, we can put this in the context of a proportion of the total history that these crystals spent in these different temperature intervals. So our initial case study for this was Mount Hood. I'm going to go through this background on Mount Hood very briefly, but essentially there's abundant evidence of magma mixing that produces the andesites that are erupted at Mount Hood. We have crystal size distributions here that, in conjunction with trace element concentrations in these crystals for the feldspar crystals, show that the andesites that are erupted have a small crystal population that's derived from a mafic magma and a larger crystal population that's derived from a silicic magma. If we focus on these, the silicic-derived crystals, most of those have complex trace element zoning patterns that are not in equilibrium with their host liquids. So we can limit the time that they spend at high temperature based on how quickly these would have diffused. And we have constraints on the crystal lifetime from the U-series ages. So the radium model ages for the two most recent eruptions of Mount Hood, is the eruption ages here, are on the order of 8 or 9,000 years. Interestingly enough, they're exactly the same. They're within uncertainty of 10,000 years, but the fact that we measure disequilibrium means that some fraction of crystallization had to be younger than that. The thorium age is discordant, rather embarrassingly large uncertainties on that age. That's because there just was not very much spread on the isochron diagram for this feldspar. But it's still useful because you still have a minimum age that you can extract from this. So the ages are discordant, requiring a combination of old and young crystallization. The minimum thorium age requires that some of the growth happened prior to 17,000 years. The fact that we preserve disequilibria requires that some of the growth happened less than 10,000 years ago, and it's consistent with a mix of zero-age rims and cores that are older than 21,000 years, but they could be much older. We can constrain the time above the rheological lockup temperature, where you go from a crystal suspended in a mobile liquid to crystals or liquid that is interstitial to a locked crystal network. And we can do that by looking at sort of melts modeling of this particular magma composition, tracking crystal mass and viscosity of the magma with temperature. And this dramatic increase in viscosity represents that transition from a liquid magma to a crystal mush that's relatively immobile. And then the diffusion times at various temperatures that we can tolerate mean that we couldn't have spent more than a few decades or to a few centuries in that time window. Out of the total 21,000 year crystal history means that the time above this locking temperature is a fraction of a percent up to maybe a few percent of the minimum crystal age. So that implies that these crystals spend most of their time in this sort of cold storage condition. And if we look at the compilation, a lot of samples show the same general pattern. So this appears to be a very sort of robust and broad-based conclusion. We're in the process of testing this conclusion out at other systems to try to see if this really comes into play. So I just want to finish by saying that there's been a whole lot more work with accessory phases in volcanic rocks because you can measure them in situ and the analytical procedure is a lot simpler. So here's a compilation of accessory phases. Each one of these lines represents somewhere between 10 and 100 analyses for a given sample in a given eruption. And then these represent PDF peaks that are primary or secondary. And the significant things that come out of this are simply that everywhere you look when you're measuring crystals in volcanic rocks, you see a significant pre-eruptive resonance. That is, a significant difference in the age of the crystal and the age of the eruption. So that implies that this kind of cold storage and recycling of material is, if not ubiquitous, it's certainly common in volcanic systems. And that's mostly interpreted as recycling from a mush or a young pluton. Okay, I think I'm out of time, so I will skip how we connect that with deeper scale chemical information and simply say that all the evidence that we have points to a picture that looks something like this, rather than a picture that looks something like this. But the challenge now is to take this and actually quantify things like how does the chemistry of this magma reservoir change from one part to another of the reservoir, or from one single part of a reservoir over the course of the history of the reservoir system. All right, thanks.